and for links at 100 megaparsecs to ensure that you get at least one count per event. And here, the orbital period is in the range above a kilosecond, up to about 100 kiloseconds. Obviously, you want shorter orbital periods because then you can see repetitions. And here, the time of the event goes up as you go that way. So you're kind of fighting, you know. You'd like to be down here because you'd like to be able to see it many times, but up here you have higher magnification and longer lasting events. So it's kind of a fight, you know. What are you optimizing for? Well, we just have to take what nature gives us, but we can, you know, at least see what we might hope for by looking at a graph like this. And the very interesting feature is that these are the systems that we can see long before merger at potentially at X-ray wavelengths, both because you might detect the X-rays at all times and also because they would be lensed. These are the systems that LISA would detect gravity waves from. So that means that at the very least, links, if there aren't a lot of these, and LISA would be working together in this epoch.
It's the vertical axis on the right, the probability.
Exactly,
So
yeah, and that's one of the things we're fighting, right?
So how many systems do we have up to 10 megaparsecs?
Well, the rate calculation right now, if we just look at black holes, tells us that under the least optimistic situation, there might just be one or a few of these things within 100 megaparsecs, so you would need links. But that doesn't include the fact that there may be many binaries that will not merge in a Hubble time, so they're not included in the measured rates, but they would be detectable this way. And it doesn't include neutron stars. And also the duty cycle needs to be taken into account. So we can't really say, but it seems like it's something that could definitely be seen with links, and if conditions are favorable, perhaps earlier with Chandra. So again, I'll emphasize the X-ray emission from many of the nearby sources would be detectable. This lensing signature requires special circumstances. As Avi pointed out, there's a probability here, which is the probability that your orientation is correct. And we're considering only systems where the orbital period is short enough that you're guaranteed to see it, because you're looking for a longer period of time than the orbital period.
Rosanne, which mass are you showing here on the x-axis?
This is the total mass. Yeah. Okay, so the take home here is that X-ray hierarchical triples are likely to exist, and I want to do a shout out to Josh here because I first started thinking about triples a long time ago due to some of his papers where he was one of the pioneers in considering this. So yes, potentially these are detectable. Now I'm going to move over to the dynamical Roche Lobe. And this is something that I didn't really think about when I was thinking about mass transfer from giants. But there is an important question. If this is the plane of the orbit, and if this is the inner binary, and let this angle be theta, as the inner binary moves, the force on a test mass at any point here changes. So if you imagine starting with a binary that has a mass m1 equal to the sum of these two masses, and m2, you can easily find the L1 point, which is the equilibrium point at which the gravitational forces exerted by these two masses is just exactly equal to the centripetal force that's needed to keep that mass not moving with regard to the co-rotating frame, the frame in which this binary is rotating, and M2, if it's filling its Roche lobe, M2 would be rotating at the same frequency. Okay, so finding the L1 point is something we know how to do.
Does that, so you're assuming that three stars are formed in the same sort of accretion distance?
No, I was just giving an example. Suppose it were a binary, then we would know what the L1 point was.
But more generally, do you expect the system
Well, by the time, we're choosing this co-rotating frame. So what we expect is this will probably be rotating at the orbital frequency, and that's the way we normally define this equilibrium point, the L1 point. Yeah. So now the point is, though, that once you don't have a single mass here, but you have a double mass, the equilibrium point keeps changing, and it doesn't even stay along this line. So the L1 point moves. How does it move? Well, in this case, I'm looking at a binary where the separation is about 20% of the total binary. The inner binary has a separation about 20%, the total orbital separation. And each one of these curves represents the motion of the L1 point. In this case, when MA and MB have the same mass, it moves along a circle. And I don't want to take the time now because I want to tell you about a couple of other things, but I could actually show you a very simple way of figuring out how you can determine approximately where these points are. I'll spend a little bit of time. If the binary MA and MB is located here, when those two masses are lined up, then you have a force which is greater at the old L1 point than would have been the force from M1. So in order for you to find the equilibrium point, you have to move away from the inner binary, and that defines this. The amount you move away may be different if A is on this side and B is on that side. In fact, the one that's less massive won't make this move as much. So when there's an extreme mass ratio and B contains only 20% of the total mass, then when you're in the configuration where B is here and A is there, you end up there. So the motion is through a double loop. It goes like this, like that, and like that. In the case I'm showing you, this is 8%. The diameter is 8% of the total orbit. So the L1 point moves. And as the L1 point moves, it moves to places where the potential is different. And since the Roche lobe is defined to be the surface of constant potential, having the same potential as the L1 point, the Roche lobe changes. The Roche lobe pushes in when you have the maximum force being exerted, and it moves out when you have the minimum force being exerted. Gold here is the Roche lobe for the binary. And the same thing happens for other binaries. This is an extreme example. This is 0.2 solar masses, and 20% of the mass is in this component, 80% is here, and this is also in the ratio MA to MB of 20% to 80%. This shows the different locations of the Roche lobe, and here I have a short video. At least I should have a short video. Oops. Well, maybe we'll come back to that. It really shows, it's kind of interesting to see how it moves. There we go. There we go. This is 10 different orientations of the inner binary. Okay?
So then what's the ratio of center major axes? It must depend on that.
That about 20% in this case. Yeah. It does depend on that. In fact, I should mention that these effects scale as r squared. So eventually, if the binary gets small enough, you don't see these effects, right? But the really interesting thing, and this is something that was pointed out by Morgan, is that the difference in the radius of the Roche lobe compared to the star, which is constantly changing as the orbital orientation of the inner binary changes, that this actually by itself can create a flow of mass from the donor. And it turns out that this flow of mass can be very significant, on the order of 10 to the minus 6, 10 to the minus 5 solar masses per year. This is a new mechanism for generating mass loss, and it's pulsed. Now we need to check this, and that's what Sophie's simulation does for us. So I want you to look at this simulation again, but now I would like you to focus on mass that is coming from the donor, because it is that mass that is pulsed. You know, we always expected there to be variability because you have something that's rotating and m dot is different on each object, right? But this is a whole different effect. This is mass being stripped in a way that reflects the periodicity of the inner binary. This is a great example of a very simple theoretical argument being able to be realized in what is now a very simple simulation, but which will become a simulation that really helps to quantify these results for us. So I'm really thrilled with this work. So this is take home 3. That analysis of the Roche lobe shows that mass ejection from the donor can follow the time signature of the inner binary. And I haven't emphasized as much the disks, as Ramesh will undoubtedly have realized, because there's also something very interesting there. This motion of the Roche lobe will cut off the disk if you have the circumbinary disk, if you have a big separation. And so you go through ranges of separations where you have or do not have a